this second part of the extension on nuclear magnetic resonance. Here we are going to cover the practical applications, and on the right hand side on the first slide you can see one typical setup where you have your superconducting coils in order to create a sufficiently strong magnetic field, and you have some sample inside, and we would like to do now some nuclear magnetic resonance measurement. So why are we needing these huge magnets? Why do we need this extremely high field strength? The reason is that if you look at the energy difference between two states with different nuclear spin, you realize that this is a very small energy difference, and the splitting will depend on the strength of the field. So the larger the field, the bigger the splitting, and the more difference we will see in occupation at a given temperature. So this is what we actually want. We would like to have a large difference in occupation for the two states, because then we can see a change in population if we excite with the correct photon, or with the correct frequency for the photon coming in to do the excitation from 1 to 2. Obviously, if we think now of a two-state system, a saturated, so a continuous excitation would only give you an equal population in both states, because it's as likely to excite from 1 to 2 as it is to de-excite from 2 to 1, right? So typically you would do a pulsed excitation mode in order to have more population in the upper state. Now, what are we actually measuring? There are two types of relaxation that are interesting to us. These are the first one is the longitudinal or spin lattice relaxation time T1. So this is shown in these pictures here, left and right, at first at time t and then at time t plus t1. So at first, let's assume we have arrived at an equivalent or a distribution where both states, the E1 and E2, are same in occupation. So as many atoms are, or nuclear spins are up as they are down. And then we wait some time and the system can relax. So after we have given it this pulse to have this equal distribution or population in both states, we let the system relax. And obviously at a certain time, we will be back to our distribution as enforced by Boltzmann. So we have obviously more states or more nuclear spins in the ground state than in this excited state. What does excited state mean? Here, if we are talking about spins, it's the direction where the magnetic moment is opposing the magnetic field. This would be our state where the energy is higher, and the one where the magnetic moment is pointing along the magnetic field would be the state with the lower energy. So this is the relaxation time T1 that we can measure. Why is the system relaxing? Well, we have excited it to the state where we have same probability for E2 and E1 at some point, but then we have interactions of these spins with the lattice, so they are embedded in some material and they are coupled, if you want, to a thermal bath and will relax to the Boltzmann distribution eventually. This is the time T1. Now, the time T2 is the transversal or spin-spin relaxation time. This is an interesting phenomenon. If you do your excitations, then all the spins which are performing this precession movement will be at first in phase. But this in-phase behavior gets lost over time. And therefore, we will lose this coherent situation, and the time for this is the relaxation time T2. Typically T2 is much shorter than T1. It depends on the material and also on the phase, if it's in solid phase or if it's a liquid. So these are the differences here. Now, before we talk about the actual measurement, the most important thing at first conceptually, it doesn't make much sense to measure relaxation times directly from the line width, right? So if something is relaxing fast, then it's very broad in its line width because of Heisenberg uncertainty. But so instead of measuring in the frequency domain, we will measure in the time domain. And this is done via Fourier spectroscopy. And in principle, these types of measurements always work in the very same way. You send in a pulse into your sample, and then you record the behavior of your magnetic moment m, so the average of the spins in the aligning over time. This is the idea. And on the slide 52, I have, this is from a previous lecture, it's a quick collection or an overview of how a pulsed excitation can in principle change the occupation of a two-level system, right? So we don't have to go into detail here. I think it's fairly clear if you just go through these steps. The idea is that you have some electric field, and this is polarized in a certain way in z direction, and because of the interaction with this electromagnetic field, we will change the population of this two-state system, and you can see that what you obtain for the occupations or the population of level 1 and level 2, this is changing over time, and you can see it's a cosine 2 omega t, and this omega is dependent obviously on the strength of the field and some coupling term that connects level 1 and level 2. So what's the important thing here? Well, depending on the time, like how long this electromagnetic field is acting on this two-level system, we will reach a different situation with respect to population. And we will call these pulses either a p1/2 or a p pulse or pi pulse, meaning that a pi pulse is the pulse that changes the population from one state completely to the other state. And the pi-half pulse is something that we can imagine as follows. So what we are going to do is we are changing the average positioning or the average of the vector of the magnetic moment m in our system. At first, we have a static magnetic field, which is created by this very, very large and powerful superconducting coil. So this gives us our main static magnetic field. And we have now the situation that we have a spin, and this spin is having a magnetic moment because it's a charge that is rotating, as we have covered before. And so this rotating spin has a projection onto the z axis. This is its z component, and this is the only thing about this magnetic moment that is constant, right? So only the z component is constant, and this gives us some energy, or is reflected in some energy level of this nucleus. So we have these levels, one in direction of the field and one opposite of the field, if our spin is 1/2, which is typically for, or which is the case, for example, for the hydrogen atom, so for the proton. Now, what are we going to do now is the following. So even in this static field, the m vector is a vector that is changing over time, and only its projection onto the z-axis is constant. But it makes this precession movement, and we are doing now the same thing, but with respect to a different axis. This is when this other pulse comes in. And in the picture that I'm creating in your mind, think of a magnetic field now that goes into the x direction. So we have a coil that gives us a pulse and creates a magnetic field in the x direction, so that we can end up with a situation where we have caused another precession of the vector, but not along the z-axis as in the static field, but now along the x axis. We make this pulse very, very short. And we make it so short that we don't make a full turn, but just a quarter turn, or a turn by pi, which means we are turning the magnetization in its opposite direction. This is what is triggered by this extra pulse that comes in. And this is shown here on this slide 53. We call it the pi half pulse. This is the one that turns the vector. And how is the pi half turning the vector? So at first we have a magnetization, for example, in the positive z direction. And then comes the pi half pulse, which is a pulse that turns the magnetization into the xy plane. Okay, so from here into the xy plane. And this is important to us because we will build this system in a way where we have a detector which only measures a change of magnetization in the y, so in this epsilon or y direction, right? Let me repeat this one more time because it's important. So we have the z magnetic field, which is our static field, and we have another magnetic field that comes in and makes this flip, gives us this pi half pulse and turns the magnetization from the z-axis into the xy plane. And finally, we have a detector, and the detector is sitting along the y-axis, so that the x and the y-axis, they are orthonormal. So these two things, the emitter that gives us the pi pulse and the receiver, our measurement in the y direction, they are not interacting with each other. They don't have any effect on each other. So we use the x pi, we use the bx field to bring our magnetization now into the xy plane, and it does what it always did before. It will make this precession. So there is still the precession due to the fact that we are now still in the BZ field, and we are making this precession in the XY axis, plane. Okay, and while we are processing, we always get a signal in our detector in the Y direction with the frequency of this oscillating magnetic moment, and this is something we can measure in our detector along the y-axis. Now, what are we doing now? Look at what happens if we send a pi half pulse, wait a bit and then send a pi pulse, and look at the signal. We have an echo that we create because at first we flip into the plane, and then we have these interactions we are having at the moment when we do the flip. All the spins are aligned because we flip the averaged magnetic moment as a vector into the xy plane. But then we have to watch how this distribution of the actual magnetic moments of the nuclei will get normally distributed over time, right? Because the spins are interacting with each other, so we have this spin-spin coupling. And for us, in order to measure it, we give at a certain time t, which we choose, we give the second pulse, which is now a pi pulse. And when we do the pi pulse, we turn around the arrows and their direction, therefore, and so they will come together and line up exactly after the time t and give us this echo. Now, why is this so cool? The advantage of this thing is that we will now, or we are able to compare the signal strength of the echo to the original value of the magnetization before we did the 90-degree pulse. So I'm just indicating this here in this graph. The peaks, if you look at the peaks over time, they won't have the same height. And from this decay, we can derive our T2. And the big advantage here is that field inhomogeneities that you can't avoid, they are canceling out because they're always affecting all the nuclei in the same way. And the only interaction that remains and causes this reduction of the signal when you bring them together again in this echo is due to spin-spin interactions. So this is a very clever way of measuring T2 time. We use the echo principle via a combination of a 90-degree pulse with an 180-degree pulse. And we can repeat this many, many times in order to get an accurate value for T2. And finally, we come to the T1 measurement. The T1 measurement, so this means our change of the spin in its projection onto the z-axis from the excited to the ground state. Again, excited state means that the magnetic moment is anti-aligned with the magnetic field, and the ground state is the state where the magnetic moment is aligned with the magnetic field. So on the left-hand side on this slide, you can see at first our average magnetic moment pointing into the direction of the magnetic field, positive Z. Now comes our BX pulse, and for the T1 measurement we do something different. We start with a pi pulse, so we turn the vector by 180 degrees. Okay, so this is what you see in situation B. And now in C you can see the time evolution of the magnetic moment on average. What is going on? Obviously this is an excited state which will relax, and this is the time that we're interested in this time T1. It will relax to its original ground state, which is the state where the magnetic moment is aligned with the BZ direction. Now, what are we measuring? We are using again our detector in the Z direction, in the Y direction, and do the following. We come in with a pi pulse, so we flip, we go from situation A to situation B, then we wait some time. We wait and wait and wait, and then we give the system a pi half pulse to turn the magnetic moment into the XY plane. And now, due to this gyro type oscillation, we will have a fluctuating signal and can measure the magnetic moment at this time when we did the flip with this pi half pulse in the Y direction. Okay, so what am I doing now? I'm just varying the time when I do my second pulse. So I start with the pi pulse, make this flip, and then I wait some time. And then I do the pi half pulse. And this waiting time between the two pulses is something that I vary. And I measure right after I've sent the pi half pulse. I'm measuring what do I get in my detector for the magnetization in the Y direction. Because by repeating this measurement many, many times and for different delay times between the two pulses, I can again create now a curve that shows us the length of the vector, basically of the magnetization over time. And from here, through a fit, I can again get my relaxation time, this time the relaxation time T1. So here you can see it makes sense to go into the time domain for measurement in order to get more accurate results for these relaxation times. And now, in this last few minutes of this extension, we'll talk about why are we actually measuring T1 and T2? What does it give us on information? Well, T1 and T2 are qualities of for example, the proton in some specific environment. So, in other words, for a hydrogen atom which is attached to a carbon, or for a hydrogen which is attached to some other atom, we will get different values for T1 and T2. So we can basically distinguish different types of tissue or classify molecules based on this information. And there are two related applications, but which focus on different aspects. The first one is our interest in specifying a certain molecule and finding and learning about its structure. Here I've given you the example of hexaborane, which I stole from Wikipedia. So here you can see the molecule B6H10, and it compares two signals that are measured, one at 40 megahertz and the other one at 12.8 megahertz. You can see the spectrum here for these two energy areas, and we will distinguish between features that are caused by the different electric or electronic environments. Yeah, this is the in German you say the Abschirmung, and the Kopplungskonstante, which is due to the nuclear spins that are also interacting when they are close to each other. So these two effects, one is this Abschirmung, so there is a shielding mechanism going on because each nuclei is obviously surrounded by some electron density, and this will depend on how this molecule or how this atom is embedded in the molecule, right? And if you think about what happens when you put a rotating charge, which is a magnet, into a magnetic field, you will have this alignment, and you have this, in this case, because it is a rotating charge, you have the diamagnetic effect, so it will weaken the field. You have a certain type of shielding if you have sufficient electron density distribution around the nucleus, and therefore the effect on the nucleus will be reduced, and you will have a different excitation energy for this type of nucleus in this environment, and therefore you can distinguish. So this is the one effect. The other one is that if the nuclear spins are close to each other, then they will also have a certain coupling, and this is something you can see in splittings. So if you have two of them, then you have the basically another spin-spin coupling, and so if the spin is 1/2, then you have the one spin in the field of the other with two possible ways of how it can be arranged, giving you a doublet structure in the spectrum. So with this information and with the measurements you do with the nuclear magnetic resonance, you can get a feeling, or you can learn about how this molecule is built. Because, for example, if you look at the hydrogen atoms, and if you look at the boron atoms, this is why we had these different frequencies, 40 megahertz and 12.8 megahertz. You will get different structures, and you can see that in one case the spectrum is a little bit more complicated. It has more splits, and this must be somehow related to the possibilities of how the environments look like for this specific atom. So this is related to one question I have in the feedbacker slide. So I won't say more here. Think about it yourself, but it is easy to find out which one of them will be is the hydrogen and which one is the boron spectrum. Okay, and then finally, if you're interested in the details in the medical usage, I recommend reading these books, Haken-Wolf first and second, but also this other book, Benwell McCash. Unfortunately it's not Springer, so you don't have access, but I'm just saying this is a very good book, Benwell McCash, Molecular Spectroscopy, giving you a very good introduction. It's also available in German. Okay, but here, my final comments. When it comes to medical usage, we need something else which we have to add, namely we would like to know which type of tissue is where in space. So we need information about the position. And the answer to this problem is you don't use a homogeneous magnetic field, a static field, but you have a inhomogeneous field, so there is a certain gradient, and therefore the energy of a certain spin flip at a position somewhere in space depends on where it is, right? Because at a different position in the field strength locally will be different. Therefore, the splitting for the magnetic for the spin flip will be different, and so you can distinguish also with respect to the actual position of the molecule in space, and you can get to a resolution that is fine enough so that you can distinguish certain types of tissue in the human body, for example, because H atoms in bone structure are typically in a different local environment compared to H molecules in fat, for example, right? And so you can distinguish, therefore, then the fat tissue from the bone structure and so on, right? So this is the basic principle of computer tomography, where you extend the nuclear magnetic resonance through this gradient in the magnetic field, delivering you a cut through, for example, organic material, and telling you of which materials it is composed of.